All right, let's get right into it. We've all chugged a sports drink before, right? But what's the actual science going on in that bottle? Well, it turns out the secret isn't just about water. It's really about chemistry, a little bit of electricity, and what keeps your body firing on all cylinders.
I mean, really think about it. When you're out for a long run or you've just finished a killer workout, you know you're losing water. But there's something else going on too. Something that can make you feel kind of dizzy or just completely wiped out. So, what is the deal with sweat? The answer is actually this really cool mix of biology and chemistry. It involves the water in your body, the electricity that's zipping around powering your nerves and muscles, and these incredibly important tiny charged particles called ions. Today, we're going to connect all those dots.
To really see why this matters, let's paint a picture. Just imagine a jogger. It's a hot day, they're pushing themselves, they're really going for it. They're doing something great for their body, but at the same time, they're creating a pretty serious chemical challenge for it. See, as our jogger is sweating buckets, they're losing more than just water. They're losing electrolytes. And this quote from Chemistry Libre texts really spells out why that's a big deal. That loss can lead to some nasty symptoms like nausea, fatigue, and dizziness. So what in the world are these electrolytes that are so important?
To get to the bottom of that, we actually have to zoom out a little bit. We need to look at the fundamental chemistry of solutions, because this is where the magic happens, whether it's in a bottle of Gatorade or inside your own cells. We'll start with a term that sounds super technical, aqueous solution. But honestly, it's incredibly simple. It's just the sciencey way of saying that something is dissolved in water. And since our bodies are, mostly water, pretty much everything happening inside of us is happening in an aqueous solution.
And every single solution has two parts. You've got the solvent, that's the liquid doing the dissolving, which for us is water, and then you have the solute. That's the stuff that gets dissolved. So think about making salt water. Salt is your solute and water is the solvent. Simple as that. Okay, so here's the crucial part. Some things you dissolve, like sugar, are what we call non-electrolytes. They just break down into individual little molecules that float around. No big deal. But electrolytes, like salt, do something amazing. They actually break apart into positive and negative ions. And these free-floating little charges are the key, because they can carry an electric current right through the water. And that is what makes them so unbelievably important.
Now let's bring this all back to our jogger. That ability to conduct electricity isn't just some cool chemistry trick. It is literally the foundation of your body's entire electrical system.
And these ions are absolutely vital. I mean, we are talking about the actual wiring that makes our bodies work. Sodium and potassium ions are what allows signals to zip down your nerves, telling your heart to beat and your lungs to breathe. Calcium is essential for making your muscles contract, which is what allows you to move at all. And without enough magnesium, hundreds of biochemical reactions would just grind to a halt. So when that jogger starts feeling dizzy, it's because this fundamental electrical system is running low on juice.
So we know electrolytes are critical. But to study them, or even to create a perfectly balanced sports drink, scientists have to make these solutions with incredible precision. So let's take a quick peek behind the curtain at how that's done.
It is a highly methodical process. This is not just dumping powder into water and giving it a stir. Every single step, from calculating the exact mass of the solute you need, to weighing it perfectly, to adjusting the pH, it's all done with painstaking care to make sure that final solution is absolutely perfect.
A lot of the time, labs will create a really concentrated stock solution, kind of like a cooking concentrate. Then they use this simple little formula to figure out exactly how to dilute it down to a perfect, usable strength. It's really just a basic recipe for precision. So that formula might tell a scientist they need exactly 10 milliliters of their concentrate. They'll measure that out precisely, dilute it with water, and boom, they have their final product. It's that level of precision that makes it all work. Now, there is one more really important idea we need to clear up, because it's a super common misconception when we talk about dissolving things. Let's just ask the question directly. When you stir salt into water and it seems to disappear, have you created a brand new substance? Is that a chemical reaction? A lot of people think it is, but the answer might actually surprise you. That's right. Dissolving something is a physical change, not a chemical one. The identity of the stuff you're working with hasn't actually changed at all. So, here's the breakdown. In a physical change, like dissolving salt, you haven't changed what the substance is. If you were to boil away the water, you'd get your salt right back. But in a chemical change, like iron rusting, You create something totally new, iron oxide. The original iron is gone. You can't just unrust it. That's the key difference. So we've seen that these simple charged particles floating around in water are fundamental to how our bodies function. But that kind of leaves us with a bigger question, right? From the batteries in our phones to the vast oceans that regulate our climate, where else are these simple aqueous solutions, these electrolytes in water, quietly and powerfully shaping the entire world around us?